back to this paper, which mentioned earlier on, Yash Agrawal had this in Medical Hypothesis 2005. And, you know, at that time, I was like, wow, this guy's clever. I read that, and I emailed him straight away, and I said, I think you're right. I think this could be the mechanism through peroxynitrites. I'll tell you about them in a minute. You know, emailed back and said, how do we prove this? And he emailed back and said, you need to do lumbar punctures. And I thought, forget that. Nobody wants a lumbar puncture, and certainly not going to be queuing up to get one of them as a part of a research project. And also, I don't know what ethics are like here, but getting stuff through the ethics committees, if it's anything other than standard practice, it's very, very difficult to do. So we kind of shelved that and kind of gave up on it, but it kept coming up. So we were intrigued about this mechanism of action stuff, and we thought, well, we know that it does this. It causes a partial blockade of the mu receptor, and you heard about that this morning. This is slightly out of sync, so I'm going to go on to the next one. Yeah, and that causes an increase in endorphins. What does endorphins do? Well, one of the things they do is inhibit this enzyme, nitric oxide synthase, which produces nitric oxide. And that could be the way that it reduces peroxynitrites. But there may be another action as well. So the endorphins are doing this. The LDN is provoking the increase in endorphins. It's then causing a reduction in peroxynitrites. And peroxynitrites are the chemical that does the damage in lots and lots and lots of conditions, MS being one of them. Almost all autoimmune disorders, heart disease, loads of things. You get to cellular level, this is the chemical that does the damage. So it makes sense that LDN would work for a wide spectrum of diseases, and it's not specific to one thing if it's got this mechanism. Now, the same's true of endorphins. So the peroxynitrites are, and I said to my patients, you'll never remember this word peroxynitrite, but you remember ono. I said the ono, or from Scotland, the onus. The onos are the thing that we're trying to control. And it's a combination of nitric oxide and superoxide, two chemicals that are naturally produced and are not really that toxic at all, nitric oxide, because a lot of it gets absorbed into the hemoglobin and is washed away. Superoxide is a bit more damaging, but on their own, these two are fairly straightforward, but when they combine together and produce these onos, it's highly toxic, and it damages cell membranes, it damages proteins, it damages DNA, it damages mitochondria. It can lead to, it's one of the cancer mechanisms probably, it can nitrate amino acids and it can ruin the enzyme systems. Interesting that Jackie said about, the anti-aging effect of low-dose naltrexone. This may be why it does that, because as you get older, some of your enzymes become nitrated, don't work as well, becomes less efficient, your muscles get sore, and there's a lot of things that could actually make sense there. Not that I'm wanting to advocate LDN for an anti-aging treatment, but it is interesting that could be one of the mechanisms through peroxynitrites. And to make it really simple, I have this wonderful slide which shows you what happens. And it says white blood cells. Well, actually, it is white blood cells, but also it's the microglia cells in the central nervous system. These nitric oxide and superoxide are produced by quite a lot of cells. But if we just, from the immune system, the white blood cell comes up and decides to beat up and kill a virus or a fungus or a bacteria, it combines those two together to produce the onos, the peroxynitrites, and the peroxynitrite does the damage. And it's highly toxic. So we don't have a lot of it circulating in our system a lot of the time, because if we did, we'd be really unwell. So we just have small amounts. It only lasts a very short time in the system, but enough to do a lot of damage. Which leads me to the Nobel Prize that was mentioned earlier on as well. See, everybody's been making these wee mentions, and I'm just following on. The Nobel Prize, which I haven't won yet, but I'm just still watching the post. Probably need to get my study done. And this, Louis Ignarro in 1988 won this. And it just shows you that even if you're a Nobel Prize winner, you still couldn't spell healthier. So I thought I'd definitely put that up. Made me feel quite good. So I'm going to do a wee timeline here, hopefully. Yeah. In 1988, he won his Nobel Prize for work on nitric oxide and heart disease. Now, I qualified in 1983. Nobody mentioned nitric oxide to me ever. I had no idea what it was. And most people were the same. When this Nobel Prize was awarded, it was a new thing. We didn't realize that nitric oxide is one of the most important signaling gases in the body. There are now 80,000. If you put nitric oxide into PubMed, you'll get 80,000 articles. So a lot of work's been done since 1988. So that was the start of it. Now, 4 years later, he was one of three authors of again, Medical Hypothesis. That's a great journal, fantastic journal, because you can write a lot of stuff in there that you think might be true. And it doesn't have to be. You don't have to prove anything. It's an intellectual exercise. I saw a paper about LDN that was sent to me 2 days ago, that's going to be submitted for, and it's about the mechanism of action of LDN, and it's going to be submitted to medical hypothesis. So it's a great journal, I think. Anyway, Louis Ignarro was one of the 3 authors that said that maybe the nitric oxide and its metabolites were important in the pathology of neurodegenerative diseases like MS. And from then, there's been a succession of interesting but pretty, small print research going on. There was Giovanni in 1998. They showed that nitric oxide metabolites were present in the CSF of MS patients. That fitted in with the hypothesis. Cross et al. They looked at nitrotyrosine, which is the marker for peroxynitrites, and pathological lesions at post-mortem. So that fitted in. Whoops, go back one. Some animal studies showing that the ONOs damaged the nerve cells. And nitric oxide doesn't seem to damage them, but the ONOs were damaging, producing MS-like lesions in these animals. 2002, Calbrese et al. They found inducible nitric oxide synthase, the enzyme that produces it in MS patients in the CSF, and they found nitrotyrosine, the marker, in CSF, which was what Dr. Agrawal was probably talking about. We needed to do lumbar punctures to measure this, because it was all done in lumbar punctures up until recently. Danilov looked at again, nitric oxide was present in all the different types of MS, but particularly increased in relapses. Fits in again, an increase in the ONO production during a relapse. Redrek et al., I'm going to come back to that one because that is a paper that's merits a slide on its own. 2006, more research showing that peroxynitrates were present in both acute and chronic MS. 2007, nitrotyrosine, the marker, was found in MS lesions. And this year, there's been some publications, 2 or 3 publications already, looking at the fact that peroxynitrates, ONOs, were produced by brain cells, by glia cells, and were also damaging 2 oligodendrocytes into different nerve cells, producing damage to axons and to nerves themselves, as well as the myelin sheath, but not nitric oxide. Nitric oxide seems to be fairly, well, nitric oxide is such an important signaling gas that we've got to be able to deal with that, and we've got a mechanism to deal with nitric oxide, and in itself, it's not damaging. I want to come back to this one that was published in the Neurology magazine, Redjak et al. They looked at nitric oxide metabolites in the CSF. They correlated this with the density of the number of lesions in MRI scans, and it correlated well. They found, and this is really interesting, that the level of nitric oxide metabolite was not related to disability. So a lot of people who were not greatly disabled had high levels. But when they followed them up 3 years later, the ones with the highest level of nitric oxide metabolites had the greatest severity of disability. They had deteriorated the most. And it correlated with MRI appearances again. So this was a really, and this same author produced another paper this year which looked at what's called nitrosative stress, and they found that this was associated with sustained disability in MS. So what this was telling us was that actually we've got something here. If we could measure this, then we could intervene at a much earlier stage and say, you need active treatment now. This is what we think. So back to the trial, we thought it is vital that we measure these nitrotyrosine levels. How are we going to do it? It could be a key to understanding the mechanism. If we understand the mechanism, it's an awful lot easier to sell this treatment if we say this is how it works. And this is, this is the research to show this is how it works. It's an awful lot easier to get people and other doctors interested in it. We know about endorphins. They're well increased. But is that the only mechanism? Or do they reduce the nitric oxide levels? The paper I read the other day there was actually looking at superoxide and thinking that was more likely to be the mechanism by which LDN would reduce the damage in MS. So there's a lot of interesting stuff there. So how do we measure the ONOs? Well, we went onto the internet and said, I wonder if there's an ELISA test, a blood test that you can do. Nobody's doing it, but is there a blood test? And there in the biotech companies, quite a lot of them have got nitrotyrosine tests. So this is a simple blood test, and you can measure nitrotyrosine. This is a nitrated amino acid that only really is present when you've got peroxynitrites and ONOs there. So it's a stable biomarker for this ONO, and it did look as if it was a potential candidate, and it was measurable in CSF, but could we measure it in the blood? This is what we did.